Hello guys, so we are going to continue the discussion with respect to statistics, and in this video we are going to discuss about central limit theorem. Now, central limit theorem is a very important concept to understand some important things like what is sampling distribution, what are the properties of sampling distribution, and how you can also use it in the further case like to calculate probabilities, area under the curve. We'll also discuss about that. So first of all, let's go ahead and understand the definition of central limit theorem. Now here it says that central limit theorem relies on the concept of sampling distribution. Okay, we'll read this statement, understand the definition, and then I will be showing you with detailed examples and all. Okay, so central limit theorem relies on the concept of sampling distribution, which is the probability distribution of a statistics for a large number of samples taken from a population. Please make note of this kind of important point, right? Of samples taken from a population. The central limit theorem says that the sampling distribution of the mean will always be normally distributed, as long as the sample size is large enough, regardless of whether the population has a normal, Poisson, binomial, or any other distribution. Still, we have not discussed about Poisson binomial distribution. We have discussed about normal, but just understand this Poisson and normal distributions are a distribution of data which does not follow a Gaussian distribution. Okay. Now let me make you understand with the help of examples and what this entire statement basically says. Let's consider that I have a specific random variable which belongs to a normal distribution with some mean value and standard deviation value, right? So whenever we have this property, obviously what kind of bell curve you will have. So you will basically have this kind of bell curve. Okay, and this we specifically say it as a Gaussian distribution. This is for the scenario 1 when your distribution follows a normal distribution. So here you will be able to see this will basically be my x of I, this will be my mean of x, right? The mean, population mean. So let's consider this as my population data. Okay, population data. Now what we will do is that, now here you can basically see that central limit theorem relies on the concept of sampling distribution. Okay, so let's say if this is my population data and this is how it is plotted and this follows a normal or Gaussian distribution, if we consider some sample data, so from this let's consider that I want to create some sample data like S1, S2, S3, S4 up to Sm, right? And this sample data size, let's consider some n value. This n value in the case whenever your population data is a normal distribution, it can be, this is basically the sample size. It can be of any value. It can basically be of any value. So let's consider this S1. So in this S1, I may select X1, X2, it may get selected X4. Like this, we are just taking some sample data from the population data. And this will basically be Xn. Why n? N is the sample data. And then after this, we go ahead and compute the mean, the sample mean of S1, right? Similarly, in X2, we will go ahead and probably select different elements. It can be randomly selected like this. And this will basically be my sample mean of 2, right? And similarly, what we can do, we can select X3 bar. We can have different values. And finally, I'll be having Xm bar. Okay. So like this, what we are doing is that from this population data, we have selected some sample of some sample size, and this n value specifies our sample size, right? And n value can be anything. N value can be anything if your random variable follows a Gaussian distribution. Now, what does central limit theorem say? Now, let's go ahead and read this. Central limit theorem says that the sampling distribution of the mean. So here I have actually got the entire sampling distribution of the mean. Now, what I will do, I will take up all this mean and plot it. And once we plot it, here you will be observing that according to central limit theorem, again, see this. The central limit theorem says that the sampling distribution of the mean will always be normally distributed. So if we take this x1 bar, x2 bar, x3 bar till xm bar and we plot in this particular way where this is my x bar and this will be my mean of x bar, you will be seeing all the data points will be falling here and there, and it will probably follow a Gaussian and normal distribution. I'll not say probably, it will definitely follow a Gaussian and normal distribution. So this is nothing but this is a sampling distribution of mean. Sampling distribution, right? So here you can basically sampling distribution of the mean. So this data will basically be following a Gaussian and normal distribution. So this is what a central limit theorem says. Again, let me repeat it. A central limit theorem says that the sampling distribution of the mean, of all the mean, right, from this particular population that we have selected as in the form of sample, will always be normally distributed as long as the sample size is large enough. Now this n, why I'm saying it can be of any value, because this is following a Gaussian distribution. Now this is where I come to the second scenario. In the second scenario, let's consider there is a random variable x and it does not follow a Gaussian distribution with some mean and standard deviation, right? So in this particular way, what may happen is that our distribution will not follow a Gaussian distribution like this, right? It will not have a bell curve, but it will be somewhere like right skewed or left skewed. Now in this particular case, if I do the same thing, and here my n value should be greater than or equal to 30. Specifically, my sample size should be greater than or equal to 30 in order to this particular, basically, like if my n size is greater than or equal to 30, then if I probably pick up some S1 samples and calculate the X1 bar, S2 sample and calculate the S2 bar, and if we take this sampling distribution with respect to XM bar, and if we plot it, then you will be seeing that then this will also follow a Gaussian distribution. All this sample will also follow a Gaussian distribution. This is what a central limit theorem states. Okay. Now see, coming to the next statement over here, right? Regardless of whether the population has a normal distribution or Poisson or binomial or any other distribution, the sample distribution of the mean will be normal. In this case, the n value, only when your random variable is not following a Gaussian distribution, then your n value should be specifically greater than or equal to 30. Okay. So again, let me repeat it. Very simple two conditions that I have explained over here. If your random variable is following your normal distribution, let's consider this is my population data. Now, if I create a sampling distribution with some n sample size, right? And the n value can be any value for a normal distribution, for a random variable to be a normal distributed, right? And in this case, if we take all this sample mean and if we plot it, it will follow a Gaussian or normal distribution. This is what is possible with the help of CLT, right? CLT theorem states that, okay? It has proved that, okay? We don't have to go inside the proof, but again, if you probably consider, if you pick sample of data, if you do this, you'll be able to get it also, okay? And let's say if your random variable is not following a Gaussian distribution, it can be of any other distribution. And here in this case, my n size should be greater than or equal to 30 for making sure that whatever sample mean I take, here we probably get in the form of Gaussian or normal distributed, right? So this is what a central limit theorem states that, okay? So let me just go ahead and again read it. The central limit theorem relies on the concept of a sampling distribution, which is the probability distribution of statistics for a large number of sample taken from a population. The central limit theorem says that the sampling distribution of the mean, whatever mean we have calculated, will always be normally distributed as long as the sample size is large enough, regardless of whether the population has a normal, Poisson or binomial distribution. When I say Poisson or binomial, it is basically not following a Gaussian distribution. Okay. Now this was one very important statement that we can probably come up with from the central limit theorem. Now the other thing that we can probably come out, okay, this is also very much important. Okay. So first thing, whenever, let's say I have a normal distribution of the population, right? Normal distribution of the population. Now, whenever I have this, you will be able to see that I will be getting this kind of bell curve. This will basically be my x and this will be my mean. Now, in this scenario, my random variable will belong to a normal distribution with some mean and standard deviation. But once we do the sampling distribution out of this, so obviously, you know, with respect to sampling distribution of mean, right? Once we do this, right, of some n value, right, n small n value, and the outcome, you know, that once we plot this mean, it will again follow a bell curve. But what will be the mean value? So this will basically be my x bar and mean of x bar, right? Now in this scenario, here initially my mean was mu and my standard deviation was sigma, right? Once I do this sampling distribution, will my mean change? Or will my mean be something else? Or will my standard deviation will be something else? So central limit theorem also says that once we do a sample distribution of a mean from a population data, my x will definitely belong to a normal distribution. And here my mean will be equal to the population mean. So this is nothing but my population mean, whatever population mean I had. Okay, whatever population mean I had. But my standard deviation will be equal to sigma by root n. What is n? N is nothing but the sample size. N is but nothing but the sample size, and sigma is nothing but population standard deviation, right? So this is what central limit theorem also says, that whenever you are probably picking up sampling distribution of a mean from a population data which is normally distributed, then the new mean will be obviously equal to population mean, will be approximately equal to population mean, but your standard deviation will be nothing but standard deviation divided by root n, and this standard deviation is nothing but with respect to the population standard deviation. So this is the specific changes that are basically happening whenever we take sample distribution of a mean from a normally distributed data.